Welcome back. Let's jump right into this explainer, where we decode the world through mathematics, from ancient myths straight down to everyday shapes. If you've ever stared down a Cambridge mathematics paper, yeah, I'm looking at you, 0580 syllabus warriors. You know math isn't just about crunching isolated numbers. It's about spotting patterns, modeling reality, and proving universal truths. Today we're going on an incredible journey through some seriously fascinating mathematical investigations. We're going to see how the exact same logical thinking applies whether you're trying to prevent the literal end of the world or just trying to wrap a present without wasting half the paper.
Here's what we're looking at today. First, the legendary Towers of Hanoi. Second, the geometry behind tiling the stunning Alhambra fountains. Third, modeling gift wrap area to optimize everyday objects. Fourth, similar shapes and scaling. And finally, we'll master tangents and circle theorems. Let's get into it.
Section 1. The Towers of Hanoi. The math behind the legend.
Our first stop is an ancient Vietnamese legend involving a temple, a group of priests, and a massive puzzle that supposedly dictates the end of time. The myth goes like this. Inside this temple stood 3 giant rods. On one rod, there were 64 golden discs stacked in descending order, the biggest at the bottom, the smallest up top. The priests were tasked with moving all 64 discs to another rod, keeping that exact same order. And the kicker? The legend states that the moment the task is completed and that last disc is placed, time ceases, and the world comes to an end. Pretty high stakes, right?
But it's not a free-for-all. The priests are bound by just 2 very strict rules, which takes a simple physical stacking exercise and transforms it into a beautifully complex algebraic pattern. Rule 1, they can only move 1 disc at a time. Rule 2, a disc can only be placed on top of a larger one. You can absolutely never put a larger gold disc on top of a smaller one. Because of these constraints, you can't just pick up a chunk of the stack. You have to constantly shuffle discs back and forth across the 3 rods just to free up those larger ones at the bottom.
So the crucial point here is finding the algebraic formula for n discs. And we do that by investigating the smallest number of moves needed for smaller stacks, like 2, 3, or 4 discs. If you map it out, 1 disc takes 1 move. 2 discs take 3 moves. 3 discs require 7 moves. Bump it to 4 discs and it jumps to 15 moves. Do you see the pattern emerging? The smallest number of moves is always exactly 1 less than a power of 2. So for n discs, the absolute minimum number of moves is 2 to the power of n minus 1.
Now, let's apply that newly discovered formula back to our legend. The priests have 64 discs. That means they need 2 to the power of 64 minus 1 moves. Now, imagine the priests are moving incredibly fast, like 1 disc per second. Compare their required time to this massive number, the 4.54 billion year age of our Earth, and you'll quickly realize we aren't running out of time anytime soon. Moving 64 discs at 1 move per second would actually take them roughly 585 billion years. To put that into perspective, the entire universe is only about 13.8 billion years old. It's a gorgeous demonstration of how intense exponential growth really is in algebra.
Section 2. Tiling the Alhambra fountains, geometry in Spanish architecture.
Let's jump over to the Alhambra Palace in Spain and see how this builds into real-world architectural modeling, specifically looking at pool borders. By comparing a very specific pool setup to a generalized variable shape, we can deduce an algebraic rule for the exact number of square tiles needed for any border. Take a look at this specific example, an 11 by 6 unit pool with 2 by 2 unit squares removed from the corners. That takes exactly 38 border tiles. But think about it, architects don't want to recount individual tiles every single time they change the pool size. By labeling the pool's dimensions as m and n and those corner cutouts as x, we can create a universal algebraic rule for the total tiles, t. It's all about shifting from a basic counting exercise to a powerful generalized mathematical model.
And this brilliantly illustrates how even the hidden little spacers placed between those decorative tiles follow strict algebraic rules based purely on a wall's dimensions. When putting up a tile wall, tilers use little cross-shaped spacers for 4-way intersections and T-shaped spacers for the edges. If you investigate a grid that is L tiles long and W tiles wide, the number of cross spacers and T-spacers is entirely predictable. Finding these rules, that is exactly the kind of investigative mathematics that connects the algebra you do in the classroom to professional architecture.
Section 3. Modeling gift wrap area, optimizing everyday objects.
Scaling down from grand Spanish palaces to our everyday lives, let's look at the mathematical efficiency of wrapping a present. As you'll see, different flattened nets of the exact same 10-centimeter cube require entirely different minimum rectangular areas of paper to cover them. See, A 3D cube can be unfolded into a 2D net in several different ways. If you lay these nets out on a rectangular sheet of paper, the bounding box, the actual rectangle of paper you need to cut out from a roll, changes dramatically based on the shape of the net. Even though the surface area of the cube itself remains totally constant, the wasted paper around the edges of the net changes significantly.
We can actually extend this logic beyond just cubes to any cuboid. If a cuboid has dimensions of p by r, we can map its net right onto a rectangle. For manufacturers wanting to produce paper sheets within a specific area range, say 2,000 to 4,000 square centimeters, applying this exact formula, area equals 6p times the quantity of p plus r, optimizes the dimensions. By graphing this function on a display calculator, manufacturers can instantly pinpoint the exact dimensions of a box that fits perfectly into their existing paper supply limits, which virtually eliminates waste. It's a real game changer for production efficiency.
Section 4. Similar shapes and scaling, from cones to troughs.
Okay, let's dive into what happens when we scale 3D objects up or down using strict mathematical proportions. Whether you're calculating the capacity of a trough or enlarging a cube by a scale factor of 2.5, understanding the relationship between linear, area, and volume ratios is absolutely vital. Here is the golden rule you have got to remember. If the linear scale factor between two similar shapes is k, then the ratio of their surface areas is k squared, and the ratio of their volumes or capacities is k cubed. So think about this. If a water trough is scaled up by a factor of 4, it doesn't hold 4 times as much water. No way. It holds 4 cubed, or 64 times as much water. Grasping this exponential jump in volume is essential for everything from engineering design to reading blueprints accurately.
Section 5. Tangents and circle theorems, the rules of the circle.
Finally, we're going to strip away the physical models and look at pure geometry. In many exams and real-world engineering puzzles, circles are the ultimate test of geometric reasoning. Let's look at one of the most elegant proofs out there. Because the internal triangles created by the radii are completely congruent, any two tangents originating from a single external point will always perfectly match in length. Imagine a point hovering just outside a circle. If you draw two straight lines from that point so they just graze the edges of the circle, those are your tangents, they will hit the circle at the exact same distance from your starting point. Why is that? Well, if you draw lines from those touch points to the center of the circle, you create two identical right-angled triangles that share a hypotenuse. The math is literally foolproof.
Building on that concept, these 3 foundational circle properties discovered through dynamic geometry serve as your absolute cheat sheet for solving complex puzzles. First up, the angle on an arc at the center is always exactly twice the size of the angle at the circumference. Second, angles drawn in the same segment of a circle are always equal. And third, if you have a 4-sided shape completely touching the inside of a circle, what we call a cyclic quadrilateral, its exterior angle perfectly equals the interior opposite angle. Get these locked in your brain. So, using all the rules we've just covered, can you deduce these final angles, complete the puzzle, and conquer the geometry? If you have tangents meeting at point X, you know those tangent lengths are perfectly equal, which creates a neat isosceles triangle. You also know the radius meets a tangent at exactly 90 degrees. So, if the internal angle OAB is 38 degrees, you can cascade these rules, just taking it one logical step at a time to uncover every single missing angle in the diagram. You see, math isn't just a collection of separate, isolated rules. It's a unified toolkit. From the exponential growth of ancient golden discs, to calculating the exact paper required to wrap a box, to the unseen lines governing a simple circle, the logic always holds true. Which of these mathematical frameworks will you see in a whole new light today?